In this video, we'll review the PDF of strain to failure analysis of composite. Also go to this website, it's exactly the same. Alright, and I'll be using this website to talk about things later on also. So the key issues with this thing is two cases. Alright, there will be case A and case B. So what it is talking about is that because your composite is made up of a certain certain matrix and certain fibers, alright. So therefore, when you pull this thing, okay. So which one will fail first, and what is the strength of the material, alright? Because when you pull this one, because the fibers and the matrix are different materials, so either the matrix may fail first or the fiber may fail first. Okay, so I repeat again, is either the matrix can fail or either the fiber will fail first. So either one will fail first. Okay, so when you pull these things, alright, they have a certain strain. Alright, a certain strain. I should say that there's a change in length. So change in length divided by the original length is actually called a strain. Okay, so different materials will have a different ultimate strength. Ultimate strain. Ultimate strain means that the last bit of length you can pull before it breaks. Okay, so for example, if you have your material like that, alright, and then you start to pull, it reach here, and then you start to pull, it reach here. So over here, this is the ultimate strain, for example. Okay, so you start to pull until this point, then after that it start to break, then die already. Alright, and therefore this is the ultimate strain they are trying to say. So this is how much you can pull before it breaks. Alright, so the ultimate strain is how much you can pull before it breaks. Alright, and therefore there is two scenarios. One is that the matrix is lousier, so this means that the fiber can pull very long time, but the matrix, when you pull a certain amount, it will break. Alright, this is for case A, where matrix is lousier. For case B is where the fiber is lousier. Alright, so take note of that. So case A is for matrix that is lousier. Case B is when fiber is lousier. Alright, and therefore using this understanding, let's talk about the case A first. Alright, but you should take note of something before we go on into the graph, is that it is assumed that both the matrix and the fibers deform elastically and subsequently undergo brittle fracture. What it means is that you have your stress strain curve. Alright, this is the strain, this is the stress. Alright, so it will go elastically, is a Hooke's law. Alright, so it's the strain, I forget what's the Hooke's law already. Yeah, it's this one. Okay, so it's behaving elastically. Yeah, not going into very detail. Alright, so we are talking about only materials that are elastic, that's all. Okay, and therefore it will fail brittly. So brittly means that once it reach here, it will straight away fail. It will not like being deformed or whatever. Okay, it will straight away fail and die. Okay, and therefore this is what it's trying to say. So therefore we are only looking at a very simple composite system, that's all. Alright, and therefore let's take a look on case A, when your matrix is actually a lousier, having lousier strain. As you can see, this is matrix ultimate, this is fiber ultimate. Okay, so your fiber is stronger than your matrix. So therefore, if you were to take a look, if I start again this thing, alright, maybe I should take this graph out. Okay, let's start off with the first step. Alright, so this is the stress on the individual fiber. Okay, so if you were to have the matrix also, as you can see, the matrix, the strain is much lesser than the fiber, right? In other words, if you take a look, this is for the matrix, right? So the matrix will fail at this point. Alright, it will fail at this point, okay, which is lousier than the fiber, right? The fiber will fail at this particular point. Alright, so the matrix will fail first before the fiber, which is what we have said in the case A, right? Matrix is lousier, okay, and therefore as you can see, the matrix is lousier. Alright, so knowing these things, then how do we go on next? Alright, let's take a look. So next, alright, so the overall composite stresses, because your fiber is having this particular stress strain curve, matrix is over here, so the in between is actually like that. Okay, it's by the rules of mixture, which we have often been saying, But in terms of stresses, this is the stress in the one direction. So one direction means that you're talking about a fiber when you arrange in this. So this is the one direction, this is the two direction. This is what it's trying to say. Okay, and therefore this is your amount of fiber. Alright, volume fraction of your fiber. This is the volume fraction of your matrix. Alright, so it's 1 minus fiber because you only have fiber and matrix, that's all. Okay, but nonetheless, this is the rules of mixture type of thing. I think you kind of know the things, but nonetheless this is the overall composite strength. Alright, and for the stress for the fiber and the stress of the matrix. So in between is the overall composite strength. Okay, so I hope this is pretty clear. So therefore when you have this, so after that you know that over here after this point the thing your so-called your material will fail, right? You will see some sort of failure, and this type of failure, right, is determined by if happen that the fibers fracture before the entire load is transferred to the fiber. So what it means is that because you have a lot of fibers, right, so some of the fibers may actually break beforehand. So over here this may not be necessarily breaking at this point, so is the fiber is a failure. Wait, let me take back my words. At this particular point, or at this particular point, there is two scenarios. Okay, so the first scenario is when if happen that the matrix will fail first. Alright, so maybe the first scenario is with matrix fail first. Alright, the second scenario is if the fibers fail first. Alright, so just now what I've been saying is with the fiber fail first. Alright, but let's talk about the matrix fail first. Okay, so therefore if the matrix fail first, then the stress in the one direction of your composite will be the volume fraction of the fiber and the stress of the fiber. That's all. Okay, if you remember correctly, alright, previously we used the rules of mixture, right? This is when everything is nice, nothing spoil yet. Alright, the matrix is the matrix, the fiber is the fiber. They are all working fine. Alright, but if happen that the matrix will have to have crack first, alright, then the most of the loads, alright, will be more focusing on the fiber itself. Alright, so at first the ultimate strength, not ultimate strength, the stress it can take is stress 1, which is in terms of this thing. Alright, so if happen that if the matrix were to fail, then this part is ignored. Alright, it's easier to know, right? I mean, it's easier to see already, right? So therefore this fiber will take place as the new somewhat ultimate stress of the material, so to speak. Alright, amount of stress that it can take. So therefore this is when if the matrix were to fail first. Alright, so if the fiber were to fail first, then what is the scenario then? Allow me to explain again so that it's way too clear for you and it will be good. Alright, so this is the rules of mixture. Alright, this is the amount of fiber, volume fraction of the fiber, this is the volume fraction of the matrix. This is stress of the fiber, stress of the matrix. And this is the stress in the overall one direction. Okay, this is the two direction. Okay, these are the fibers and the matrix altogether. So if happen that if your matrix were to fail first, then the case 1 is that, alright, this term over here is for this one. Right, if the matrix were to fail first, then most of the load will goes to the fiber, and this is why the fiber is taking in the overall stresses. Alright, but however, if the fiber were to fail first, then this is another scenario. Alright, so over here this thing is kept the same. Your matrix is still using the ultimate strength of the matrix, well, however, this thing over here will start to talk about the failure onset of the fiber, because your fiber is already break. Alright, so for example, if one of this fiber is broken, or few fibers is broken, then you're going to talk about the new stress. Alright, so this FMU is when if the failure of the fiber starts to occur. Alright, when the failure starts to occur, this is the amount of stress that the broken fiber can take. Alright, so the broken fiber as compared to the normal fiber, as you know, it's different already, right? Because the broken fiber is weaker than alright, and therefore it will contribute to a weaker composite, and therefore you need to know this type of thing. So this stress FMU, alright, is actually this term, alright, is the stress in the fiber at the onset of matrix failure. Alright, don't take note that this is also when the matrix also starts to crack already. Okay, so hopefully this is pretty clear. I'll somewhat stop around here, but I'll just need to repeat again in order for you to fully understand what is exactly going on. Alright, so yeah, this is for the case A if the matrix is weaker than your fiber. Alright, so this is the stress strain curve of your fiber, and then this is the stress strain curve for your matrix. And then using the rules of mixture, you will know that the overall composite, alright, is this one, this line. Okay, the amount of stress it can take. So it's actually this one, the rules of mixture. This is stress 1. Okay, hopefully this is all clear. Alright, so therefore within this case A there is two scenarios. If it happens that the matrix will fail first, alright, this matrix will fail first, then all the stresses will actually go to the fiber, right? And therefore if the matrix were to fail, then you will go like this. Okay, if the matrix will fail, then you'll go like this. And since the matrix will fail first, right, so this is why it will go stagnant a while. And once it reaches once the matrix is fully weakened, alright, the fiber will take in the load totally, and this is why over here it starts to grow. Alright, then as you can see, the curve is parallel to the fiber curve. Alright, hopefully this is very kind of clear to you. Alright, and therefore if happen that if the fiber were to fail first, alright, then you're talking about this line only, alright, which is this one. So you all the way go in this straight line. It's a constant one, I believe. From the graph it's like that lah. So therefore you just need to know all this. Alright, so this one, this one, the rules of mixture. And if the matrix were to fail first, alright, then you'll go stagnant, and after that the fiber will take in the thing, and then you'll start to grow. Alright, if the fiber were to fail first, then you always be like that, that's all. Okay, you always be like that all the way. If fiber fail first, alright, if fiber fail first, if matrix were to fail first. Okay, hopefully this is clear. I hope that this is way all clear, and I think this is it for case A, I think. So this case A is only talking about if the matrix, so-called the ultimate strain, alright, of the matrix is lousier than the fiber. So the fiber can be pulled longer, or in a sense. Okay, and therefore in the next video we'll talk about case B, where now the matrix is actually somewhat, the ultimate strain is stronger than the ultimate strain of the fiber. Not stronger lah, but rather than longer. Yeah, so I think, yeah, see you there.